An important goal in chemical kinetics is to develop a mathematical equation that describes the rate of a reaction, or how fast the reaction goes, based on the concentration of the reactants, how much stuff you put in there. Take, for example, an industrial application. I want you to imagine that an industrial plant has a large reaction chamber. We need to have mathematical equations that describe how fast that reaction goes, because if the reaction goes too fast, there may be some downfall to that. Maybe the reaction releases too much heat too quickly and things might melt or explode. Or if you don't introduce enough of the reactants, then the reaction may go so slow that it may not be practical and may not actually even occur in a reasonable amount of time. So our goal is to develop a mathematical equation, and we're going to use a hypothetical reaction where we have reactants A and B reacting to form a product, C. And our goal is to write a rate law equation. The rate of the reaction will depend on a rate constant times the concentration, the brackets is molarity concentration of the one reactant raised to its order, times the molarity concentration of the other reactant raised to its order. Is it a first order response, second order response, zero order response? So to do something like this, we're going to perform experiments, and in front of us we have a table of experimental data where this reaction was performed 3 different times, 3 trials. In the first trial, we have concentration of A is 0.1 molarity, the concentration of B is 0.1 molarity, and experimentally determined that the rate, the speed of the reaction, is 5 molarity per minute. Now, we want to repeat that experiment where we alter just one of the reactants, the concentrations of only one of the reactants. Analogous to, imagine you're a physician and a patient's coming to you with multiple medications. You only want to alter one medication at a time to see the effect of that specific medication. In this case over here, we're going to perform the trial 2. We're going to repeat this experiment, but you'll notice that now we have doubled the concentration of A while keeping the concentration of B constant. And we notice that there is a difference in the rate. So what is the order of reaction with respect to reactant A? To do that, we're going to compare the rates of 2 trials where only A changes. And that's going to be trial number 1 and trial number 2. Where only A changes. Now, I like to prefer to put the faster rate on the top, on the numerator. So this is going to be, we're going to look at reaction rate from trial 2 to rate of trial 1. And in rate in trial 2, we're going to use these reactant concentrations. The concentration of A was 0.20. The concentration of B was 0.10. And in trial number 1, the concentration of A was 0.10, and the concentration of B is 0.10. Now, the rate of reaction trial 2 was 20 molarity per minute, and the rate of trial 1 was 5 molarity per minute, 5.0. We should be correct with significant digits, so that's 20 with a decimal point there. Molarity per minute equals K. Let's do the K for the numerator, K for the denominator, but hold on a second here. The K's cancel out, and the concentration of B is the same, so 0.1 to the Y and 0.1 to the Y cancel out. So now we have 0.20 to the X over 0.10 to the X. And now 20 over 5, that's 4. And this is the same as 0.2 over 0.1, which reduces to 2. raised to the x power, right? There's 0.2 over 0.12 to the x. And so now we have to ask ourselves, what is that exponent? And this, in this case here, the exponent is going to be equal to 2, because 2 raised to the 2 power, right? 2 to the 2 power is 4, and that is what we're looking for. We're looking for the order. So the value of x is going to be 2. So I'm going to come over here. We know that x is going to be equal to 2. Now let's compare the rate of two trials where only the concentration of B changes. And we're going to look over here, and we're going to see trial number 1 right here, and trial number 3 right there. You'll notice that the concentration of A remains the same, the concentration of B changes, and the rate changes. So we're going to do the rate of trial 3 over the rate of trial 1. Now we're going to plug in numbers. Trial 3, the concentration of A, right here, let me erase this for right now. Here's trial 3. The concentration of A was 0.10. The concentration of B was 0.20. And then in trial 1, right here, the concentration of A is 0.10, and the concentration of B is 0.10. The rate in trial 3 was a value of 10 molarity per minute. And the rate of trial 1 was 5 molarity per minute. And the K's cancel out over here. The 0.1 to the x and 0.1 to the x cancel out. So now I have 0.20 raised to the y power over 0.10 raised to the y power. And we'll simplify this, 10 over 5, that's basically 2. And then this is 0.2 over 0.1, which is 2. And this simplifies to 2 to the y power. And so now what is that exponent? In this case right here, so 2 is equal to 2 to the first power. Y is equal to 1. So we have x equals 2, y equals 1. And here we go, y is equal to 1. And so now our final answer is rate is equal to K times the concentration of reactant A to the second order, second power, times the concentration of reactant B to the first power. But it's understood that we don't need to put that 1 over there. I'll go ahead and erase that. Because you'll see it written without that, but that's first order. And so now we've determined our general rate law equation. In the next video, we're going to take a look at how to find the value of K, a numerical value for K.